Okay, so we are continuing with from the last point that we have left. Last time we have discussed stationarity. Actually, we have concluded the stationarity discussions. So we have two different types of stationary processes. The first one is stationarity in the joint PDF sense and stationarity in the moment sense. This was previously discussed in the last two lectures. And we made a definition, wide sense stationarity. So this is W, S, and S, wide sense stationarity. This is a rather practical definition. It's easy to check. So this means stationarity in the moments, but only in the first moment and in the second moment. Okay? This is called wide sense stationarity. If I satisfy stationarity in the mean condition and stationarity in the autocorrelation condition. Now, this was last time. So today we start with an example. So this is our example. Find the processes below are wide sense stationary or not. Okay. Number one, let's check this one. X of t is A times t, where A is uniformly distributed in 0, 1. Actually, we have studied this. This is the random slope signal, random slope. Okay, random slope signal. So for wide sense stationarity, I should check number one, mean function. So what is mean function? Expected value of x of t. Okay. So after the expected value operation, so this is with respect to, if this is t1, this is t1, a specific time. This is a random variable. That random variable is expectation. But from the definition of the random process, this is equal to expected value of a times, let's say, t1. But let's solve it for a generic t. Okay? For any t, this is valid. So what is random over here? A. So this is with respect to a. Then this becomes expected value of a times t. So what's the expected value of a? 1 over 2. Okay? So I get t over 2. So what's the conclusion? Well, we see that this is not a constant. So for wide sense stationarity, this should be a constant number, a fixed quantity, like a DC signal. Okay? So we see that then x of t is not stationary in the mean. Hence, not wide sense stationary. So I don't even need to check the autocorrelation because both of them should be satisfied. Okay? This is example number one, the first case. Now let's have the second case. The second one is, again, a familiar example, x of t. So again, I'm using both notations as you see, capital letters sometimes with tilde. But for example, when we come to theta, so what is the capital letter for theta? So this is small theta, by the way. So capital letter for theta is something very difficult to draw, something like that. So you would appreciate that I couldn't draw it very well on the board, so this is the reason that I'm including these tildes, by the way. Okay. Also, it emphasizes what is random, isn't it? Because, you know, a capital letter, but who knows? Is it the amplitude random? I mean, so I emphasize it like that. So I repeat the same story. Now this is theta, uniform distribution 0 to pi. What was this? Random phase cosine. Again, we have covered this. Okay. So number one, mean function. So I think it's clear. Mu x of t is expected value of x of t. This is expected value of a times cosine omega t plus theta. Do you agree? So what is this expectation? Actually, we have calculated this. This was 0. Exactly, this is equal to 0. Okay. So if you don't remember this, it's easy to verify because we are integrating over theta. This is uniform distribution. So assume this is a constant value for now. integrate this thing with respect to theta in 0 to 2 pi. So you are integrating, finding the full area of a cosine, area under the cosine in a full period. This is what we have said. Okay. So for these simple integrations, do not evaluate these integrals. So this is actually calculated in, let's see, lecture 30, if details, around 8 minutes. Okay. Or this is page 19 of our notes. Page 19. So this is constant. Okay, so there is some hope that this is White-Sands stationary because it satisfies the first condition. Now the second condition. So what is this one? Again, we have calculated this in the same lecture. So this is a square This was a little bit more complicated, but if you check our notes, let me write the results. Let's do not do the calculation one more time. Cosine omega t1 minus t2. Now, the condition for stationarity in autocorrelation is this should be a function of t1 minus t2. So it shouldn't be a function of two variables, t1 and t2, independently. This should be a function of a single variable, t1 minus t2. Okay? But only difference is that I'm taking the difference of the products and passing through this function. So can I write this as a function of difference? Well, obviously, this is the a square cosine omega times the argument is this function. So this also satisfies this. So we see that this is indeed White-Sands stationary. Okay. But no surprises. Well, no surprise. Why it's a no surprise situation? Since previously we have seen that, random phase cosine is strict sense stationary, SSS, strict sense stationary. So do you remember we were giving that discussion? Strict sense stationary means it is stationary in the joint PDF for any degree, first degree, second degree, third degree. So if you sample it, let's say at endpoints, their joint PDF is stationary. So it's stationary in the strongest possible sense. So of course this implies this. But we are right now checking the conditions, let's say individually. Maybe we don't know this, okay, in this calculation. Now the third one. Now I should be erasing this part. Number 3. Now this is something new. This is something that you haven't seen before. Well, k is equal to, let's say, minus infinity to infinity, ak e to the j omega naught kt. So what is random? Ak is random. So ak is 0 being, well, independent random variables. Okay, AKs are, these variables are like that. So you can say that at the birth of this process, if I want a realization of this process, how do I realize this? I come up with an infinite length vector. That infinite length vector is containing these AK values from, let's say, a minus infinity to a plus infinity. Then I insert it over here and sketch this function. This becomes the realization. It's exactly like this one. The only difference is that right now there is only a single parameter. So to give birth to this process, or to give a realization of this process, I'm generating a single pick from this distribution. Right now I have to know realization of these infinitely many numbers, or parameters of that, let's say, function, to generate a realization of this process. So you see that I don't know anything about the distribution, because the question is only check the White-Sands stationarity. Okay? I will be calculating expectations. Maybe this will be enough, who knows. So do you remember such a relation from earlier courses? What is this thing called? Maybe you'll remember if I write it like this. Fourier series, okay? This is the Fourier series. So this is a periodic function with fundamental period t, am I right? Periodic function with the fundamental period t, and only difference is that the Fourier series coefficients are random. So you see that at the end, if I make this realization, I see something periodic. A periodic function with period t, but the coefficients are random. Okay, let's see. Number one, expect mean function, expected value of x of t. So I should take the expected value of this. So how about if I write it like this? Would you agree? I think you will. Do you agree with this step? So I take the expected value of x of t, expected value is over here, then I have a bunch of terms summed over here, then expectation of individual term is this. Okay? So this is linearity of expectation. Of course, you can worry about whether this sum diverges to infinity or not. But assume that everything goes right, it does not diverge to infinity. That means that I can do such a calculation. So what is this result? Again 0. Why it is 0? Well, all AKs are 0 mean. So this is 0. So I get 0. So good news, this is constant. Or bad news. If it is not constant, this will be end of this example. Now I have to check the autocorrelation function. So now, actually good news, don't worry, this is an important example. So what is the autocorrelation definition for, as you see, this is complex valued right now, okay? So because of this J. So I should be using this definition. Last time, at the end of last lecture, lecture number 31, we have defined this. So this, you will see, this conjugate will be critical. Don't forget this conjugate. If you are dealing, this is a definition for autocorrelation for the complex valued quantities. Okay, I have a complex valued random variable over here. So what do I mean by a complex valued random variable? Maybe this is random, okay, but it has a real part and imaginary part. Okay, that is it. So this J, you may also consider it like 2 points x, y. Both of them are random. You may consider it also like that if you wish. So the issue is, now their joint distribution is the issue, but at the end you get either a complex number or a vector if I know the joint distribution of real part and the imaginary part. Okay, so complex valued random variables is not something very complicated, as you see. Now I should do this calculation. Well, this shouldn't be very complicated. Let's see. Expected value of xt1, this one, if I make a mistake, just let me know. Okay, I have this, times let me have more area over here. And I don't like the, let's say, tone of that marker. Let me get another one. So this is omega naught k times t2, this. Do I have a mistake right now? I have a mistake. Conjugate. Number one. Do I have one more mistake over here? Yes, I have one more mistake. Because this is a dummy variable for this summation, isn't it? K is a dummy variable. At the end, at t1, I get a number. So this is the Fourier series. Evaluated at time 1, I get a number. So I have dummy variables the same. This is a problem because right now I have k. This k refers to this summation or that summation. We shouldn't do that. Okay, so I should write first summation index, dummy variable is k1, let's say. And this one is k2. Okay, something maybe obvious at this level, but let's just mention that. So I have two summations. At the end, I get expected value of AK, AK1, and AK2, e to the j, omega naught. So what do I have? K1, and is this correct? I get this. Do you agree? Do I have a mistake? Well, conjugate. I'm always, as you see, making the same mistake, perhaps. Do we agree? If I conjugate this, there is a conjugate over here, there is a minus sign over here. Now, do this product, two summations, okay? Move the expectation in. I have, maybe I should write K2 also, K1 also over here, okay? I have K1 times K2 under expectation, okay? And the remaining term is this, plus that, after conjugation, this becomes minus. Okay, now the issue is, if I can calculate this, my problem is solved. Because, that is the only expectation, as you see. The rest is like summation. So what do you expect for this one? That part. So that is expected value of A, K1, K2 conjugate. So I will write something like this. If K1 is not equal to K2, what is the result? Maybe I should also point as independent random variables. So what is the result if they're independent? 0. The reason is this would be expected value of AK1 for independent random variables. This is the expected value of AK2 conjugate. So this, of course, AK1, AK2 random variables over them. Okay. So if I have independent random variables, I have such an expectation result. So this is the nice thing about expectations. 0 times 0. I think this is 0. Overall, this is equal to 0. How about the upper one? Now this is the other case. K1 is equal to K2. Then this is the expected value of, when they are the same, expected value of AK1 square. Magnitude square. Because when they are equal, this becomes the magnitude square. And I should calculate it over AK1. So how can I write this? How about writing it like this form? Expected value of AK1 magnitude square times Kronecker delta K1 minus K2. Actually, this is a side result for this calculation. So do you agree that this is equal to this? So this is like an if statement. Do you remember? This is Kronecker delta. Kronecker delta means that if the argument is equal to 0, example, if delta n minus 1, how do you sketch this? As an n. Something like this, am I right? It's everywhere 0. If the argument is 0, you have 1, like an if statement. If statement. If the argument is non-zero, you have 0. So if the argument is 0, that means K1 is equal to K2. You have 1. Okay, K1 is. If they are not equal to each other, so this multiplies, you get 0. Okay. So this is the nice thing about our notation. Of course, I'm erasing this part. Now, I have evaluated this right now, and I will continue from this part. K1, K2, expected value of A, K1 magnitude square, times delta K1 minus K2. Am I right? So this is this part, which is this part. Okay. Then e to the j omega naught K1 T1 minus K2 T2. So how can I evaluate this right now? Now I will do the following. I will be, well, all K1 terms is taken out. So there is also something over here. So I'm left with this, K2 delta K1 minus K2, and I have this term, e to the j j omega naught k1 t1 k2 t2. Okay. So if you run this summation from minus infinity to infinity, what do we get? So this is always equal to 0, isn't it? So this with respect to k1. Sorry, this with respect to k2. So I'm changing k2. k1 is fixed somehow. So when k2 happens to be k1, then this is 1. Otherwise, it's all 0. So in this summation, all terms are equal to 0, except the term when k2 is equal to k1. Okay? That is it. So this is equal to e to the j omega naught k1. k2 should be equal to k1. k2 should be equal to k1. Okay, this is equal to this. So at the end, I get this. k1 minus infinity to infinity, expected value of a k1 magnitude square omega naught k1 t1 minus t2. So this is the end. We cannot go any further than this. So this is just a number. And this is my final answer. So what was the question? So this is the mathematics. So you should learn this mathematics. So what is the critical thing? The conjugate is, as you see, very important, because otherwise I will never have this minus. So I will never get t1 minus t2 at the end if I don't have the conjugate. Number two, this calculation with Kronecker delta, like the if statement interpretation, it was very helpful for the evaluation of such a thing. Of course, you can, by considering what you are doing in this summation, you can also get the same result. But if you use this, it becomes very systematic. Okay. Now the question is whether this is a function of t1 minus t2 or not. Is it a function of t1 minus t2? Well, it depends only on the difference. Okay? It's a complicated function. So it's a Fourier series one more time. But it only depends on t1 minus t2. So if this, call this z, for example. There are a bunch of numbers over here. So this is like a periodic function in z. So that function of z is the function that we are looking for. Of course, assuming that this summation converges, it makes sense. So indeed, this is a function of t1 minus t2. This is also satisfied. So what's our conclusion? White-Sands stationary. So this is okay. It's indeed White-Sands stationary. That is the end. So this was our third example on this issue. Okay. So any questions on this calculation? So again, this is just carefully executed mathematics. As you see, we don't need even the density information. The information that I need for this calculation in the third example is just this zero mean and being independent. That was it. Because at the end, I'll be calculating moments, as you see, and that was what I need. Okay. Now, this is the end of stationarity discussions. Now, I would like to discuss a very important type of process, Gaussian processes. Gaussian process. So let me introduce this by writing the definition. X of t is called a Gaussian process if its nth order joint PDF is jointly Gaussian distributed. Okay. So maybe you haven't seen this joint Gaussianity. Let me catch that. Okay. So first of all, do we understand this? This is a random process, x of t. something like that perhaps. But we haven't calculated its density. So this was just Weissen's stationarity. It says that this is talking about joint PDF description, nth order joint PDF. So this is talking about the form of the PDF. If the form of the PDF is something very special, I mean, no surprises, Gaussian and Gaussian, then we call this a Gaussian process. But this should be valid for all n. Okay? Nth order joint PDF for all n. Let me write it over here. For all n values. Okay? Then jointly Gaussian distributed. Now the next question is, what is Gaussian distribution? If I have more than one variables, what is Gaussian distribution? So probably, I don't know whether you have seen it or not, but this is something very fundamental. So this is the definition of jointly Gaussian distributed random variables. This is always given in any textbook, but since it's a little bit complicated looking, maybe you didn't pay much attention to it. So what is this? I have n random variables, n of them. This is this n, nth order. Okay, so this is their joint density. It has a rather special form. So what is that rather special form? So it is, this is a matrix. It will be this matrix. This is a vector. Now you can ask, where are these variables on the right hand side? So this is a vector. So I'm subtracting two vectors. Okay. So the first vector is the x vector. So this contains the elements of this vector are x1 to xn. What is mu x? Mu x is the mean of these random variables. I have n of them. Okay. What is Cx? Cx is actually covariance matrix. This is called covariance matrix. Maybe with Ahmet Hoca you have studied such things. So what is covariance matrix? I can explain this a little further, but the ij entry of this matrix, maybe fifth column, sixth row, or fifth row, sixth column. Okay? x5, x6. So this is the covariance of two random variables. This is calculated, so this is a pairwise operation. Covariance of, for example, 1, 2 is written in the 1, 2 entry of this. Covariance of 1n is written in the first row and column of this matrix. Okay, covariance matrix. So pairwise covariances are written in this matrix, and so on. Now we take the inverse of this matrix for this calculation. So this inverse is obviously important. So let me just to refresh your memory, what happens when n is equal to 1 over here? This should be reducing to standard Gaussian distribution. So can I see this? So 1 over 2 pi. So why do I have this power to the n's and so on? To make it the area, I should say volume under it should be equal to 1. Because you see many. So 1 over 2 pi to the power 1. So what is this? Cx. So this is a 1 by 1 matrix because I have only one entry, 1 by 1 entry. So this is, let me write it like this. So this is covariance of x1 and x1, which is the variance. Sorry, let me write it a little better. Variance. Okay. So there is square over here. Okay, there is square root over here. Okay, let's be patient. Then on the numerator, I have e to the minus 1/2 x1 minus the mean of it. And covariance matrices, as I have said, is just this. Inverse of this is 1 over sigma 1 square. And I have the same thing also over here. So it's like square. Okay. So this is the standard, what we call normal distribution or Gaussian distribution over here. So you didn't ask me, but what is this operation? So actually this is equal to determinant of, you calculate it, there's lots of operations as you see. Determinant of Cx is square root, let me write it clearly. Okay, determinant of Cx is square rooted. This is very complicated looking, but if you look at the details, the way I remember this is, I generalize it from the n is equal to 1 case. For the higher cases, well, we will be saying more things. Okay. Now, what does this say? This says that if I have a random process, x of t, so let's try to understand. So from this x of t, if I generate n samples, like this, okay. If I generate n samples like that, it says that it doesn't matter how many samples that I generate for all n, their joint PDF. So their joint PDF can be written in this form. Okay? So their joint PDF will be written like this. So very special type of distribution. So this time we are defining the distribution in a reverse way. For example, I was telling you random process, defining you like this, and I was, for example, asking what are the joint PDF description of it. So this is the opposite. So joint PDF description of a random process is given, and this is given for all n's. And we call any process having such a description whose samples are jointly Gaussian distributed. Their joint PDF is Gaussian distributed, as you see over here. Then we call this Gaussian process. I have repeated this many times, sorry for that, but that is the definition. So what are the important consequences of this? So I should write some notes. Note number 1. Notes. If we know the mean function, what was the mean function? Mu x of t. And covariance function, what was covariance function? I can write it like Cx t1, t2. Okay. Of a Gaussian process, so that is, I know the moment, first two moment descriptions. First two moment description. It is possible to write joint PDF of x of t for any n samples. Do you agree? A little interesting, because I was saying that, okay, these moment descriptions, they are easy to calculate, but they are not very valuable because joint PDF includes more information. I was telling you such things, indeed. But assume that you have n samples, and you know that those n samples are distributed according to this. So how do you write this joint PDF? I need to find the parameters, isn't it? Parameters of this density. For example, for the Gaussian distribution, n is equal to 1. So there are only two parameters, mean and the variance. So if I can find the mean and the variance, I know the form of the distribution. I'm done. There is nothing else to do. So what are the parameters of this distribution? So it's interesting that the parameters of the distribution are the moments. So this is a parameter. If somebody tells me this vector, I can insert it over here because I know the form. It's a Gaussian process. So this is this. So if I know this one, this is a vector, I'm done. So how about this covariance matrix? This is a matrix. I don't know this matrix, but so if somebody tells me this covariance function, then do you think I can calculate this covariance matrix? Let's think. For example, let's say that x of t5 is my random variable x5 and x of 6 is t6, okay? And I have n of these random variables. So in that covariance matrix Cx, this is a big matrix perhaps, it's an n by n matrix. But here is the case. There is a fifth row, 6th column entry. So this will be the fifth row, 6th column entry. So this is 5, 6. This is covariance of x5 and x6 should be written over there. Okay? So how can I calculate this? Well, this is the covariance of these two random variables. But this is the covariance function. Okay, there is some abuse of notation, I agree. But let me call this Cx. Evaluated at T5 and T6. Because this, covariance function is for all times. Okay, if I know that function for all times. That means that I can fill in this matrix entries simply from this covariance function. I can fill in the entries of this mean vector. This is easier to see because x1 is x evaluated at t1. From the mean function, there is nothing else to do. Okay? I know all the parameters of this Gaussian distribution. So Gaussian distribution is somewhat special because moments of this distribution are also its direct parameters. Okay? So if you know the moments, first moment, second moment, covariance, you can insert those information like in this case, in the one-dimensional Gaussian, standard Gaussian distribution, you can write that. So let's read this sentence one more time. If we know the mean function and covariance function of a Gaussian process, that is, I know the first two moment descriptions, it is possible to write the joint PDF of x of t, this Gaussian process, for any n samples. Is this clear right now? So this is very interesting. So this tells us that now finding these moments, first two moments, is sufficient to fix the density if the Gaussian process for the Gaussian processes. Now let me write another comment. Comment number 2. So if the processes, now it's a little bit more interesting, White's and stationary and Gaussian, i.e. mu x of t is constant, then Rx T1, T2 is equal to, well, okay, this is a function of, let's say T1 minus T2, okay? It's a function of T1 minus T2. So let's remember, what was Cx, because I need covariance function. This is Rx T1 minus T2 minus mu x T1, mu x T2, but this is just constant. This is C, this is also C. So I have C squared over here, essentially. Okay? So this is difference of two Rx T1, T2 can be written as a function of the differences of the arguments. White's and stationarity, as we have seen. So what can we say? Then, this is the implications left side. Then x of t is, what's going on? So point number one says that if I know the mean function, covariance function, I can say something about the densities. Now, a specific mean function, always constant, a specific covariance function or autocorrelation function, this is also another function, let's say T1 minus T2, okay? Then what can I say about the distribution? So you can see that x of t is in this sense, strict sense stationary. So the reason is, well, if you look at this PDF, then this PDF only depends on T1 minus T2, differences of these times, okay? Or T3, differences of these evaluation times. Let me explain. Since joint PDF depends on the time differences between the samples, i.e., there is no need for an absolute sampling time information. Okay? So actually, this vector is always constant. I mean, it's not changing at all. This vector is always constant. So there is a function, there is a parameter, a vector, a matrix over here, this. And this is only changing by, as you see, difference of the arguments. So that enables that if I sample it with an offset time, these n samples, it doesn't matter because their difference, sampling time, difference will be the same. Last time again, in the last 2 hours, we have discussed this. Okay? Stationarity in the joint PDF sense depends on this. Maybe I should write it one more time, but if I have samples like this, x1, xn, stationarity in the joint PDF means the following. If I subtract this, if I delay my original samples by delta seconds, I get this. So this requires that. So if I select my delta, this requires for all delta. Last time we have discussed this. When delta is equal to, let's say, T1, so this becomes 0. This becomes T2 minus T1. This becomes Tn minus T1. So as you see, if the process is stationary, I have this. So this is the reverse argument. I know that this distribution depends only on the differences. So I write this, I go there. And that's the proof of stationarity in the PDF, okay, for this one. Well, think about it. Maybe this is a little bit complicated because we have just introduced this covariance matrix. But if you focus on only this covariance relation for 2 samples, I think you will see that this matrix is not changing. If I add an offset to my sampling times, that matrix will not be changing because this covariance matrix has the entries calculated like this. So if you add an offset of delta seconds over here, then in this covariance calculation, it doesn't matter. That's cancelled. So that matrix stays the same. Okay. Very good. So this is rather remarkable. Why? Because Weissan stationarity, it was something easy to calculate. It's maybe I can estimate these mean function, autocorrelation function, etc. So if I can do Weissan stationarity, I'm getting stationarity in the strict sense. It's very interesting and good news. So you may say that why are we worried about Gaussian distribution? Because, you know, this has some nice mathematical properties, but is that the only reason? So let me write my third comment. So the third comment is why Gaussianity is important. So number one, well, probably you will remember by central limit theorem. at the beginning of this course. This is very important. If we have summation of, let's say, n independent random variables, roughly speaking, then the sum converges. Well, there are details in distribution to Gaussian distribution, to Gaussian random variable, because I'm talking about this. This is called the central limit theorem. Okay, so it's something very simple. Well, assume that you have an antenna, so you receive a signal at time t1. Okay, maybe there is some noise over here. Noise is A. Plus, maybe your neighbor is also using his cell phone. Your neighbor is also sending you some interfering signal. Maybe you are moving. Because of your movement, there is some other reflections and so on. You receive some other signals. At the end, there is some galactic noise. You add up these things. Okay. So if you have several independent, let's say, contributions to your observation, independent contributions, these can be noise, signal, jamming, interference, etc. Okay. So this can be at the molecular level even, molecular level. Okay. Doesn't matter. At the end, you get a Gaussian distribution. Okay. And there was an example Ahmet Hoca was showing that we reached almost like Gaussian distributions even if you convolve, let's say, 3 of these PDFs, 4 of those PDFs, etc. Okay, it's almost like Gaussian. So this is a fundamental result. This is the reason that we see Gaussian distributions all the time coming up in literature. For example, even in the university entrance exam. So there are several groups of students. There are many factors affecting the students, and they are always distributed in Gaussian shape. What do I mean by Gaussian shape? Well, if you look at this Gaussian distribution, they are coming from different areas. They have different properties. Maybe exam conditions are a little bit different. So that is affecting the student's performance. At the end, if you look at the whole distribution, if you take the average over all Turkey, let's say, now you see that these distributions are, because of these independent effects, they are Gaussian distributed. Okay. If you don't see a Gaussian distribution at the end of this exam, you should be a little bit suspicious because that means that there is some cheating going on. Everybody is getting the same answers. Okay? Then you have everybody is getting the same answer. There's a peak over here. Okay. That is the case. Gaussian distribution naturally comes up. Summation of these independent contributions. Number 2, so if we process x of t, a Gaussian process, a Gaussian process x of t with an LTI system, linear time invariant system. Actually, linearity is sufficient. Linearity is sufficient, but let's think about, as an electrical engineering student, let's think about LTI for now. LTI system, that is time invariance is not needed. Okay, but I want to say it for LTI, a specific case. Then, the output process, that is, let me draw it over here, x of t, h of t, y of t. Guess, what is y of t? Yes, exactly. This is also Gaussian. It's not very surprising, isn't it? Because, this kind of summation of so many effects, and there is also linearity, superposition, summation kind of effects. So Gaussianity is preserved. Yt is also Gaussian. So Gaussianity is preserved. Under linear operation. Now, this is very important for us because at the input of your antenna, you have a Gaussian distribution. Then you design a filter, low-pass filter. Then at the output, you have a Gaussian distribution. Okay, Gaussian process. Okay, if you take a sample, it becomes Gaussian distribution. Okay, so that is the reason. So Gaussian processes are naturally coming up, And if I do LTI kind of operations, filtering, etc. and etc., I again see Gaussian distributions. So what is nice? So these Gaussian distributions can be expressed by only if I know the mean function and the covariance function, or autocorrelation function, because I can get the covariance from the autocorrelation function, doesn't matter. If I know these two, lots of things. So for the rest of the course, we will do the following. I know the mean and autocorrelation at the input. Filter is fixed, let's say. What is the mean and the autocorrelation at the output? Okay. I will try to calculate such things. And if I know that, if the input process is also Gaussian, then I can calculate the output mean and the autocorrelation. From this fact, this will be also Gaussian. So this will be enabling us to find, I'll be just keeping the track of mean and the autocorrelation through this processing chain, filtering, 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 etc. I'll be keeping the track of mean and the autocorrelation, and that will be it. So as we have said, calculation of mean and autocorrelation, it shouldn't be very difficult. Okay? So we will see how we can do this. Now, let me see what else do I have for today. Okay, I will continue with an example on Monday, but that's all for today. Thank you very much.